Such a wonderful question, truly great. Took me 1 minute to close my laptop and sleep. Oh, I think this might have been sarcasm.
Oh.
Medium, my ass. I didn't read this one.
Only to be some path. Return the city that with the smallest number of cities that are reachable through some path. Okay, so what we can do is a Dijkstra's algorithm from every single node. We can do a Dijkstra's algorithm to figure out all the nodes that are reachable within some k path. And then once we do that for every single node. That would be like a n. So if we do that for every node, Dijkstra's algorithm would be probably n log n, or yeah, it would be like depends on how much edges, but let's say, yeah, chat, what are y'all thinking about doing a Dijkstra's algorithm on every single node? But I'm wondering if that's the most efficient way to do this. This has such a high rate, but do you see why I'm thinking of using Dijkstra's or no?
Yeah, yeah, it makes sense.
Have you studied Dijkstra's before?
It's, yes, I have, but I've forgotten it, so I need to review it. But I see, because you need to find the shortest path to that neighbor, and it can take like a roundabout way that isn't the direct, like, expensive path. So if you're still you're doing the solution where you're doing Dijkstra's on all the nodes, right?
Yeah, that's one approach. I'm just trying to think of one way that's simpler. I guess we can do Dijkstra's here, and if we can reach a node, I wonder if we need to even do Dijkstra's on every single node. I mean, I don't know if it's gonna make it faster, but this is like not a good thing to do. What's Paul saying? N cubed. Yeah. I mean, what I'm thinking is a Dijkstra's algorithm on every single node. Maybe we can just go implement that. Have you ever done Dijkstra's?
I have, but yeah, I've forgotten it. I would not be able to do it from memory or anything. I would probably like, yeah, no.
To figure about this.
Okay, I imagine it's some kind of like we search all the neighbors of every node that we encounter. We keep a set of the nodes we visited so that we don't like overlap over nodes we visited. And then if we actually eventually reach the target, we just like return whatever distance we've been keeping track of, like summing up. I think it's a DFS. It kind of sounds like one. I don't know though.
Yeah, we
but
could even
that's all I remember.
We could even just DFS from every single node. See if we can go 0. And then we could kind of see how far out we can go. I mean, that's one approach. I don't know. This question is gonna be a lot of code. If we do the Dijkstra's. People like this question, you're saying?
Okay, such a wonderful question, truly great. Took me 1 minute to close my laptop and sleep. Oh, I think this might have been sarcasm.
Oh.
Medium, my ass. I didn't read this one.
How did it get such a high? That's what I'm looking at the acceptance rate. I was like, if I've never seen a Dijkstra's algorithm have higher than that. I can show you how to implement Dijkstra's real quick. So from city.
Well, people are saying this question is like a waste of time. There's like some bad test cases.
Why is the acceptance rate so high? It's crazy.
Yeah.
Okay, it looks like what we're trying to do. Okay, let's implement this Dijkstra's algorithm. So I'll quickly show you how to do this one is hard though, because it's like, okay, what we're gonna do is we're gonna start at every single node and pop all of the edges onto that. Let's see what this. Um, let's just implement this real quick. I'll show you how to do that. You're watching the stream, right? 1334.
I'm listening to you on Discord, but watching the stream. So
Paul, it's
the
pretty
stream is a
high.
little.
It's pretty high. That's just yeah. Dijkstra'S makes sense, Paul. But I was thinking, yeah, all nodes is a lot of work. So what we're going to do is even implementing this is honestly I don't think they're gonna ask you something this hard in an interview, because when I already
Okay.
look at the rating, it's already higher than the usual one. But I'll write this one down. But I think let's
It
work
looked
through.
easy, but this is definitely way a little bit too hard. I think they
I'll
would
run this in the chat.
like maybe a basic graph question, if anything,
Yeah,
or a
yeah, yeah. This
tree.
is like I don't think I mean they might ask you this, but Alpha. I mean, if you want me to write it, I can write out the Dijkstra'S algorithm. Okay, let's do.
Okay.
Let's just implement it for them. Dijkstra'S, given a node. So we're gonna want to parse out all of the edges. So one thing you need to always do is build out a adjacency list. So it's gonna be a bidirectional adjacency list. So from let's just import. Let's just quickly finish this. Everyone's saying Floyd Warshall.
Yeah, that was one of the hints of that last one, to use Floyd Warshall's, I think.
So, are you familiar with building adjacency lists? That's one thing that you should be able to do real fast.
I think I saw you do it before. Is it's you have a dictionary, and then each key is the node, and each value is just like a list of adjacent nodes.
Yeah, exactly. So we're gonna loop through all the edges, right? The edges are gonna tell us what city connects to the other one, and also what's the weight. So that's important as well. So in our adjacency list, it's pretty much gonna look like we're gonna have a hash map, pretty much like this. So we're gonna say for every node is gonna be in here, and we're gonna store all the neighbors of each node, right? And then we're gonna have a list for every neighbor of each node. So we're gonna say for 0, 1 is a distance 3 away, right? For 1, 0 is a distance 3 away. And we'll store a bunch of tuples like that, where it says the node that it connects to and the edge. So what we're gonna do is we're gonna loop through edges, right? And then for the adjacency list, we're gonna say A maps to, and there's gonna be a cost. So A maps to B. So A maps to B with a cost of that, and we'll do the reverse as well, because it's a bidirectional graph, right? So A connects to B, but B also connects to A, so we need to store that neighbor. So that builds us our adjacency list. And now what we're going to do is we're going to want to perform a Dijkstra'S algorithm on this adjacency list. So we're going to be given a node and an adjacency list, essentially. And with a Dijkstra'S, you want to use a heap, or pretty much you want to use a priority queue. So we're going to use heap queue right here. And then we're gonna start off with our priority queue, right? So pretty much while the priority queue actually has elements, we're going to do a adjacency list, and we're gonna pass in the distance threshold is here as well. Vin, what's good? So now we have our priority queue, and once we have our priority queue, we're going to be looping till that priority queue is empty, and we're only going to want to push elements. We're only going to want to push elements onto our priority queue if we could actually get to that element, right? We'll do some bounds. We'll do some checks before. We're gonna only pretty much the priority queue is gonna contain cities and the distance that it took to get to that city. So let's say we start with node, and usually it only takes us since we starting at the node, we can just set it to 0 because we're just saying we're starting at 0, right? It only takes us 0 distance to get to where we want or to get to this first city. So what we're gonna do is we're pretty much going to pop out this node. So equals, we're gonna do heap q dot heap pop. So that pops, or we're gonna have to reverse this because with the heap works. It pretty much sorts the heap, or it maintains the heap variant using the first index, right? So we'll say this is our distance. So when we pop that out, that's the first node, that's the first city, and we want to maintain some sort of scene array. In most graph questions, you want to maintain some sort of scene array to avoid cycles, right? Let's go scene. Are you still here, by the way?
Yeah. So this is kind of like, yeah, so we're not going to visit a node if we've already taken care of it.
Yeah. We don't want to visit nodes if we've already taken care of it. And then we're gonna keep track of the scene cities, right? So we say our distance, we're gonna heap dot pop, and then that's gonna give us our distance, and then we're gonna say for our neighboring cities in the adjacency list, because the adjacency list essentially tells us who our neighbors are. So we're gonna look for all the neighbors in our adjacency list, and it's also gonna give us a cost right here. So pretty much if the neighbor has already been visited, just like continue, right? We don't want to deal with that case that we've already seen it, right? Secondly, if the current distance we've traveled, right now we've only traveled 0 distance, plus the cost is actually greater than the distance threshold, we don't want to visit that candidate, or we don't want to visit that neighbor, essentially. But lastly, if it actually does fit in there, what we're going to do is we're going to probably... the main thing with Dijkstra'S is figuring out when to put it in the priority queue or not. So let's just add the scene every time we visit, and then I'll optimize it after, because sometimes that matters a lot. So we have a scene set here, and then we're gonna pretty much, once we visit a node, sorry, did emoji. I do scene dot add that node that I visited, because that should have been, once we pop it out, that means I should have got there in the smallest distance possible. So basically for my neighbors, if it's in scene, I continue. If it's too far away, I continue. Otherwise, let's pop it into our heap. So let's do heap q dot heap push, and we're gonna pass it here. We're gonna push onto our heap the distance, which is distance plus cost. Sorry. And the actual node, right? And scene cities, we can probably just count here, but at the end of the day, we're gonna return scene cities. Something like that. Let's say print, and then we could just debug it. This is one way to debug it. We can say node has seen cities, something like that. So we have a priority queue, and then what I would do a lot in the interview is also just walk through the code and just make sure I'm doing everything proper. So we have a priority queue, we have a scene set, and I'm not adding, I already noticed right away, I'm not adding, I'm adding to scene set here. So we have the first node, and then I'm not incrementing the scene cities, so I'll increment it, I'll increment that by 1, but we're gonna -1 because we don't want to include ourselves. So So we're looking at the heap. We're popping. We're getting the distance. And then we're saying for our neighbors in the adjacency list, if the neighbor is already seen, that's fine. If the distance plus the cost is already greater than distance, we don't want to add it there. Otherwise, we do heap queue. Otherwise, we push that onto the heap. So since it's a priority queue, the smallest one should bubble up. So this is distance plus the cost. The distance would be 0 plus whatever it costs, so that should be 3. And then afterwards, we say, yeah, it took 3 to get to the neighbor. And then let's just run this for every single node in the graph, and then see what it prints out. Do I or adjacency list. So we pass in our adjacency list, and we pass our distance threshold. See what that prints. Wait, so see, 3 has seen, wait, it's bugged out. 0 has seen 2 cities, 1 has seen 4 cities, 2 has seen 3 cities. So I already have a bug in there. Why did it say 1 has 2 cities, 4 cities?
Maybe it's including itself.
Let's see.
Because they're all out. Well, yeah, they're each off by 1. Each of the scene cities numbers is off by 1, I think.
Okay. Let me print out the adjacency list to just make sure that I'm actually building that up correctly. So we're saying 0's neighbors is 1 to 3. You have a node in the heap multiple times the way you wrote it. Yeah. Well, yeah, you're right. He's one of the people in the chat is right. If I've seen a node already, I don't want to count it. So.
Oh, yeah.
That's why I might need to flip this. So 3 cities. Let's see. So let me adjust my scene array. See, node here. Usually I like to do the scene array out here, but sometimes that doesn't work for that case. So we'll do heap. No, this won't work for that case. Okay, what do we get? 2, 3, 3, 2. What is this? 1, 2, 2, 3. So see how we have all the different cities listed out, right? So now we just need to figure out the smallest, or what do we need to return? If return the city with the greatest number. So what we're going to do is, for every city, we're going to now, after we run the Dijkstra'S algorithm, right? After we run the Dijkstra'S algorithm, I don't know if it's going to be too slow yet, but after we run the Dijkstra'S algorithm, we're able to actually calculate how far each, or how many cities each one could reach, and that looks good. We just need to pick the one that has the largest value, right? That makes sense so far?
Just like as the tiebreaker, or
Yeah. I guess what we can do is we can probably sort it at the end. Is but um we can say results. So basically cities. So these are the number of cities. I get no, we don't need. Wait, let's see if I want to sort it at the end. But what we can do is for I in range, we can store a max result. Oh, it should be the smallest city, right? So what we can do is let's just do something easy. Yeah, like the same O is gonna be the same, but num cities. What we're gonna do is we're gonna result dot append. We're gonna pass in the I, or we're first gonna pass in the number of cities that it could reach.
mm-hmm.
Let's see. Yeah, the output here is output. Why is the output here 3? Oh, because that's the biggest. That one has the largest. Let's just see. So we're gonna do results.append, right? And we're going to pretty much we're gonna add the number of cities that it can see and the node, and then after we can pretty much sort that. Once we sort that,
Okay.
we have them in the right order. We say 0 can hit 2 and 3 can hit 2. Pretty much now we just need to figure out the largest one that's also 2.
Well, that's a cool tip. I didn't know you could sort tuples like that.
Yeah, it'll first sort by the first key, then the second key. So let's just be like smallest. We can do smallest found, and pretty much we'll just figure out. We'll just keep track of this. We'll say min of. So at the end over here, we should know the smallest found. Print is 2. Right. So basically, what we can do is we can filter out all the ones that are not equal to 2, and then we could just sort it backwards. I mean, like we're doing a few passes to it, but we could probably do one more pass to it. We could say for elem in result, right? Let's do right for element in our result if the index equals 0, or if the index is the last element is equal to the length of result. And all I'm doing is literally trying to print out this last one, but you want to basically what I'm going to do is I'm going to look ahead, or I'm going to look for the last one before it changes to something other than the smallest one that we found. So basically if the index is equal to the length of result minus 1, or because if it is, then we look at the result. So index plus 1 is not equal to Paul. Yeah, they ask it. Or the result is not equal to smallest found. Something like that. Wait, how did that return the wrong thing? 3. Oh wait. Oh, sorry. I have to do element 1. Wait. What's the result? 2 0 2 3. So if the index is equal to the length or the result. Oh, sorry. Result. Something like that. Nice. Damn, that was crazy. Are you still here?
Yeah, yeah. Wow. Okay, well, so why is there such a high acceptance rate
I have
for
no
this
idea.
question, do you think?
But I think
It's
how
like
I'd break this down is with a lot of the graph questions you want to grab and y'all, I'm a little bit off some beer right now. I'm not gonna lie. But what's it called? You need to build an adjacency list. That's like
mhm.
automatically know right away. Automatically know how to build adjacency lists in multiple ways. There's like 3 or 4 different ways that you can do it. But yeah, Dijkstra is using a priority queue. But the one annoying thing is I don't like how yeah, well, yeah, for seems to depend on how complete the graph is. But yeah, you have any questions on how I would approach that? Do you see like how I kind of would walk through it in the interview?
Mm. Okay, I think so the part about Dijkstra's that maybe I would have missed it, like if the interviewer asked me to just implement Dijkstra's straight up, I would probably forget about the priority queue because that's like not something that I carried over in my memory. But once I study it, and like some other graph algorithms, I'll probably get a better understanding of it. I had a question about like how you were debugging.
Yeah.
So let's say that I actually there's like a bug and I'm trying to find it. Like what to what extent am I what's the best way to do that, handle that during the interviews if like
Yeah.
there's like some bug I'm trying to find.
I mean, for what I've seen, only the fan companies won't let you run your code. Like Meta and Google, they'll do it on an editor and they won't let you run your code. You kind of have to walk through it and step through it. But a lot of the startups still make you finish with working code. So if you need to debug it, you can debug it the same way I did it right now, which is literally print statements. Because at the end of the day, you want it to get running code. You want to get running code by the end of it.
Okay, so if you're allowed to run it, then I guess try to fix it like with that similar process.
Yeah, similar process. Figure out like you see the way I was kind of breaking down. I was like, let me see if my adjacency list is working properly first, and then let me check all like some of the other stuff.
Can I can I would I be able to just let's say that I just implemented the adjacency list part. Could I just like stop for a moment and like check to make sure it works?
Yeah,
Is that
yeah,
okay?
yeah. You could do it. Here, let me give you another question. One good question just to see how you work with the graphs. And
Okay.
chat, if anybody wants to do a mock, just type it into. Otherwise, we're gonna keep prepping this guy up for his interview.
Yeah, thanks so much.